that we record. Cool. So the architecture of the argument was as follows. We started by thinking about the tree. And what we said was, okay, if you have a tree of a certain height with a formula at each level, that's the same as having a dividing chain of certain length. And how did that go? Well, that was just using S-indiscernible trees. We said that, okay, if you take a tree, you make it S-indiscernible, then, okay, at each level, you're inconsistent, and you're indiscernible over the stuff on the path below. So that means that you divide over it. Okay, so it's very easy to go from, okay, from the instance of a tree to the instance of dividing. Now it follows then that if you have a formula or a tree, if you have a theory without the tree property, that means you have a bound on how long your dividing chains can be. Now, using the rank, we saw equivalently that that gives us a bound in the length of our forking chains, going from dividing to to forking. Now, using that, finally, we concluded that we had local character. So if you have a type over a big set, then it doesn't fork over a small set. And from that, we were able to prove Kim's lemma. So all of that comes together to prove. Oh wait, yeah. We proved Kim's lemma. So good. So that's where we're at now. Now, what we're going to do is we're going to deduce several. Oh wait, no, we didn't do Kim's lemma. Sorry, we did one direction of Kim's lemma. We showed that. Okay, what did we show? We showed that Morley sequences exist. So I guess this summary was more for me than for you, because I wasn't sure what we had done. Okay, so it says a plugin is required to share iPhone, iPad screen. Okay, now we have the plugin. Good. Okay, cool. So here's where we were. We were at Kim's lemma. So suppose T is simple, then phi x a divides over a if and only if for all Morley sequences a over a I. You get something which is inconsistent. All right, so what did we do last time? What we did last time was we showed that Morley sequences exist. That was it. Okay, so now we need to go the other way. I mean, so, okay, if you know that Morley sequences exist, then if you divide with respect to all Morley sequences, then of course you divide. That direction is very easy. Now we need to show, okay, suppose you divide, then you have to be inconsistent along a Morley sequence. So let's do 1 implies 2. Oops, I don't need green. Sorry, I'm always a bit frazzled and making excuses about it. Last week I was saying it's because of the election, and today I gave a talk just before this, so I think my mind is somehow still elsewhere. But okay, now we know exactly what we're proving and what we have to do. So what we'll do is we'll say towards contradiction. Suppose phi x a divides over a, but there is a Morley sequence I, which is ai I less than omega over a, such that phi x ai I less than omega is consistent. Sorry. This is our assumption towards contradiction. We have a formula that divides, but that dividing is not witnessed by a given Morley sequence. Okay, so here's our first claim. Or I guess that doesn't need to be numbered. Let's just call it a claim. So the first is that for all n less than omega, a greater than n is independent over a with a less than or equal to n. So what does it mean to be a Morley sequence? Let's recall. What it means to be a Morley sequence is that if I take the nth element, it's independent with everything that came before. So on the left-hand side, in the definition of Morley sequence, I have an, and on the right-hand side, I have things less than an. Now here I've added tons more stuff on the left-hand side. Now instead of just having an, I have everything after an. So why should that be independent? All right, so remember, what does it mean to fork? It means that you imply a formula that forks. Formulas involve finitely many variables. So if this isn't true, then it involves only finitely much of a greater than n. So what we'll prove is by induction on k, at least one, we will show that for all n, a n plus 1 through a n plus k is independent with a less than or equal to n. And of course, this suffices by this fact that forking comes from formulas. Okay, so for k equals 1, this is just the definition of being a Morley sequence. Because when k equals 1, all I'm saying is that a n plus 1 is independent with everything that came before. That's what it means to be a Morley sequence. So far, so good. And now, what's cool about this argument is I think you're going to get to see sort of like why all of these like formal properties that we were working on earlier were useful or interesting. So we know, so now assume for k. So 1, we have our inductive hypothesis, which tells us that a n plus 1 through a n plus k are independent over a less than or equal to n. So this is, recall, our inductive hypothesis. And then 2, we know that a n plus k plus 1, going one more, this is independent over a with a less than or equal to a sub n plus less than or equal to a sub n plus k. So this is by definition of Morley sequence. So certainly we have both of these things. So base monotonicity, said what? It said that if you have something on the right-hand side, you can move it into the base. So this will imply, in particular, that a sub n plus k plus 1 is independent over a together with a sub n plus 1 dot 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 a sub n plus k. This is independent with a sub less than or equal to n. So what did I do? I just took the stuff from n plus 1 all the way to n plus k, and I moved it into the base. And that's exactly what base monotonicity said I could do. So let's call this one 2 prime. Now, if we look at 1 plus 2 prime, and let me zoom out so we can look at both of them at the same time. So if we look at these two things, this is exactly the situation that we saw described when we were talking about left transitivity. So what did left transitivity say? It says that if A is independent with B over A, and C is independent with B over AA, then AC is independent with B over A. So 1 plus 2 imply by left transitivity that A sub n plus 1 all the way out to A sub n plus k, that's like the first tuple, oops, together then with A sub n plus k plus 1, this is independent over A with A sub less than or equal to n. So because I know we've all slept since then, left transitivity just says that if A is independent with C over A plus B is independent over AA with C, then that implies that AB is independent with C over A. And we proved this when we in our first lecture on forking. This was the last thing we did. Okay, so that does it. That's the proof, right? Because that proves it for all k. Okay. Great. So let's call this, let's give this claim a name. So let's call this like the splitting claim. Why? Because it says that you can split a Morley sequence in half, and the end segment will be independent of the initial segment. Because this we'll use a few times today. So it's convenient to have a name for it. So we'll call it the splitting claim. Okay. So by compactness, we can replace I with a Morley sequence indexed by any other infinite linear order. So in particular, we could do it with t plus star, i.e. the cardinal, t plus, in the reverse order. So without loss of generality, we have I is equal to ai, I less than t plus, and ai is independent over a with a greater than I. Or let me say it this way, because I don't want to be confusing. So without loss of generality, we have I prime, which is a prime I. So we've replaced I with these guys. And notice it's with the reverse order. So now I have it indexed by t plus, but now ai is independent with everything that came after, because I can choose it to be indexed by the reverse order if I want. For all I in t plus, that cardinal. Then by the claim, I know that we have a, let's say, strictly, I guess, less than I is independent over a greater than or equal to I prime for all, okay, I guess we called this the splitting claim. By the splitting claim, we know that any end segment will be independent from any initial segment. But okay, that the role of end segment and initial segment switch because we assumed that our Morley sequence was indexed by the reverse order. So now we have a less than I is independent with a greater than or equal to I for all I in t plus. Okay, so in particular, we have, okay, ai is independent with a less than or equal to I is independent with ai over a for all I. This is actually the thing we need. So if I take I, then ai, which is part of a greater than or equal to I, is independent with everything that came before. That's the key point. So now we're going to come to our second claim. This proof has a lot of parts, I'm sorry. So the second claim is that for all I less than t plus, phi x a prime I divides over a and a less than I, or a prime less than I, sorry. Why? Well, so we know that phi xa divides And our Morley sequence was in that type. It had the same type as A. It started with A. So our Morley sequence started with A. So A prime I has the same type over A as A. So phi x A prime I divides over A as well. Okay, so that's a start. So if you divide over A and you replace your parameters with something that has the same type, then of course that divides as well. One way to see this is that there's an automorphism that takes A to A prime I. Take the indiscernible sequence that witnesses that the formula divides and apply the automorphism to that indiscernible sequence. Now you have an indiscernible sequence with respect to which the formula divides, but now instead of beginning at A, it begins at A prime I. So that does it. So of course, if phi xa divides, then if I replace the parameter of something with the same type, then it must divide as well. My given sequence started at A, so in particular, all the elements have the same type, and that's enough. But that's not what we needed. We didn't want it to divide over A, we wanted it to divide over A prime less than I. But we know that we can take J, which we'll call A prime I comma J, J less than omega, be an A indiscernible sequence with A prime I comma 0 is equal to A prime I, witnessing that phi x A prime I divides, i.e. we want that phi x ai j, as j varies over the natural numbers, is inconsistent. Okay, so if it divides, that's witnessed by some indiscernible sequence, we're just going to call that j. Now, because A less than I, sorry, prime, over A prime I, because we have this independence, we may assume by the basic characterization of dividing that J is not just A indiscernible, but A prime less than I indiscernible. So let's remember what the basic characterization of dividing said. Remember, I really stress this point that like when I think about dividing, I always think in terms of this basic characterization. What does non-dividing tell you? It tells you that you can upgrade indiscernibility. So if I have A independent with B, if I take an indiscernible sequence starting with B, I can move that sequence to another sequence starting with the same element such that now it's indiscernible not just over the base, but over A2. Or I can move A such that the sequence is indiscernible, but in this case, I want to move the sequence. So of course, if I move the sequence, I won't change the fact that the formula is inconsistent. So, I can move it and then relabel it and then call it J. So I can assume that the sequence that I have is not just indiscernible over A, but over A prime less than I, using independence. This is the one place that independence is used. This is where we use our claim. Okay, then J witnesses that phi x A prime I divides over A prime less than I. What does it mean to divide over A prime less than I? It means that there's some A prime less than I indiscernible sequence along such that if I move my formula along that sequence, I get something inconsistent. So J was given to me as just an A indiscernible sequence, but after applying independence, I showed that I could assume it was A prime less than I indiscernible, that means that it is indiscernible enough to witness that the formula divides over this larger set. That's the key point. And that proves the second claim. So after using independence, I could say that I found an indiscernible sequence over the bigger set, along which the formula is inconsistent, so it divides over that bigger set. Okay, so now all we have to do is take it to the hoop. So we know by our assumption towards contradiction that phi x a prime I less than t prime is consistent. So let B be a realization. Phi x a prime I less than t prime be a realization. Okay, now by local character, there is some set B, which is contained in A and all of the A primes, I less than t plus. Let me write this on a new line so I can write it larger. With B pretty small, so no bigger than the size of the language, such that if I look at the type of B over this large set, sorry, A prime I less than t plus, this does not fork over B. So what does local character tell you? Local character says no matter how big your type is, no matter how big the set of parameters, there's always some small set over which it doesn't fork. This is what we proved. It was among the things we proved last time. Okay, but as we all know, t plus is a regular cardinal. So if you have something of size less than t plus, then it can't go all the way up. It can't be cofinal. So there is some alpha less than t plus such that B is contained in A together with I less than alpha. You can't use all of the parameters. All right, then by the second claim, phi x a alpha divides over A. Oh, sorry, I should have had a prime there. I'm sorry. Phi x a prime divides over A prime less than alpha. Now, the contrapositive of base monotonicity says that if I divide over a big set, then I divide over any of the smaller sets. So phi x a prime alpha divides over B. Recall what base monotonicity says. It says that if I'm independent over a big set, then I can make the base bigger. So if I divide over a big set, then I divide over all the smaller sets. It's just a contrapositive of that. And since B realizes in particular the formula phi x a prime alpha, this shows B depends over B with A A prime I less than t plus, a contradiction. Okay, so let's draw a picture of what's happened here. So we have our sequence, which is A prime I less than t plus. And at each point here, we have a new formula. So this is like phi x A prime 0, phi x A prime 1, phi x A prime 2, and so on and so forth. So we choose some B that realizes all of these formulas. So it realizes this one, and this one, and this one, and this one, and this one. But also we know that this formula will divide over everything that comes below. And this formula will divide over everything that comes below. And this formula will divide over everything that comes below. This is the configuration we found ourselves in. So local character tells us that there has to be some subset which can't be cofinal over which I do not divide. Then all I do is I look at the next place and I observe that I divide over everything that comes below. So in particular, I divide over the blue stuff. So the fact that this point divides over everything that comes below, that's our claim 1. And no, I guess that's claim 2 actually. Sorry, claim 2. And then that contradicts local character. Okay, does that make sense? Are there any questions about this proof? Because this is like one of the reasons this is so important is that, okay, this is really the engine for proving everything else. So everything else is sort of deduced as a consequence of Kim's lemma. And also this is the feature of forking independence in a simple theory that generalizes. So when we try to talk about NTP2 theories, what we're going to try to do is we're going to try to prove a Kim's lemma for NTP2 theories. And when we try to generalize to NSOP1, we'll try to prove a Kim's lemma for NSOP1 theories. So this theorem you should regard as a very sort of fundamental property of forking in simple theories, one which is really at the foundation of the later developments, some of which we'll see today. Okay, so let's start collecting our corollaries. So there are a bajillion corollaries that we'll follow very soon. So the first one is forking equals dividing. Okay, so suppose T is simple. Then if phi x a forks over a, phi x a divides over a. So that's nice. Imagine for a moment that you want to understand in a concrete structure, like which formulas divide, which formulas fork. Now, you could write down what all the formulas look like because of quantifier elimination. But if you have to worry about, okay, what are all possible disjunctions of formulas that divide? I mean, this can get kind of gross and hard to understand in concrete terms. So the fact that forking equals dividing is really nice. It means that you don't have to worry about this distinction between forking equals dividing. You don't have to worry about these arbitrary disjunctions. Oftentimes this helps forking become more comprehensible in a particular structure. So this is like a very useful fact. We've seen, by the way, examples where these are different. Recall like the circular order. So somehow this is a proof that that's not simple. There are more direct ones, but it's one thing it says. All right, so how do we prove this? So suppose phi x a implies some disjunction. So we're going to have ci x ci, where each c x ci divides over a. So What does it mean to fork? It means you imply a finite disjunction of formulas that divide. Now, let's just call them the CIs. Let I equals AI C, let's say J, C0 J, C1 J, dot, 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 C K, C K minus 1 J, as J ranges over the natural numbers, be a Morley sequence over A with A0, C0, 0, C1, 0, dot, 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 CK minus 1, 0, as just equal to this tuple of parameters. So A, C0 through CK minus 1. So I look at the parameters here in my formula together with the parameters that occur in this disjunction. And I take a Morley sequence starting with the tuple of tuples. So I put them all together into one big tuple, and I take a Morley sequence starting with that. All right, now, suppose towards contradiction, that phi x a does not divide. Then if I look at the sequence, just at the AIs, that's consistent. Because of course, if I take an indiscernible sequence and I restrict to a subtuple, that's still indiscernible. That's easy to see. So this sequence of AIs is an indiscernible sequence over A. If my formula doesn't divide, then it means that if I move it along an indiscernible sequence, any indiscernible sequence I take, it must be consistent. Otherwise, that sequence would witness that it did divide. So this is consistent. Oops. So let B be a realization. Now, what we know is if I look at, or maybe I should switch to calling these J's just to be consistent. Doesn't much matter. Okay, now if I look at AJ, because this has the same type as the original tuple, this will prove the disjunction of the CIs at the jth stage in the sequence. So phi x aj implies the disjunction over I less than k of the CIs, where I replace the tuples with CIJs. Why? Well, because they have the same type as A C0 through CK minus 1. And since this was true of A and C0 through CK minus 1, it has to be true of AJ and the CIJs. This is just because they all have the same type over A. So there is some I, which I'm going to write as a function of J, less than K, such that if I look at the ijth disjunct, B realizes it. Okay, so let's just think of what's going on. So I have like A0, A1, A2, A3, so on and so forth. And at each stage, I have some finite number of disjuncts. So this is like C00, C01, C02. It's like C. How did I index these? I guess this is C10, C11, C12, and so on and so forth. Now, I know that at each stage, I have to pick one of the disjuncts. So at the first stage, maybe I pick the second disjunct. I know that my formula implies finitely many. It implies the disjunction of this finitely many, so any realization will have to pick one. So then maybe I satisfy this one, and then maybe I satisfy this one, and maybe I satisfy this one again. So ij just tells me at, if I look at the jth formula, phi a j, which disjunct must I satisfy? B was chosen to be a realization. It satisfies one of them because the formula will satisfy a disjunct just in case it satisfies one of the disjuncts. So ij is the name for that. So by the pigeonhole principle, there is a I star less than k and infinite set x contained in the natural numbers such that ij equals I star for all j in x. So as I'm going through my list, I'm looking at which disjunct do I satisfy. Maybe I satisfy the first, then the second, then the first, then the third, then the fourth, whatever. Because there are only finitely many choices, and I have infinitely many formulas, one of those disjuncts has to be satisfied infinitely often. So now, if I look at Ci star j in x, this is a Morley sequence. In the type of Ci star over A. If I take a Morley sequence and I restrict to a subtuple, that's still a Morley sequence because it's still independent and it's still indiscernible. Hence, Ci star x Ci star j as j varies through x is inconsistent. Why? By Kim's lemma. If a formula divides, then it will be inconsistent along every Morley sequence. This formula divides by assumption. It was one of our formulas, our finite disjunction of dividing formulas. We took a Morley sequence, and that means that if I restrict attention just to that disjunct, it has to be inconsistent. But it is realized by B, contradiction. Okay, so that means that phi x ai I less than omega is inconsistent. Hence, phi x a divides over a. So we started with a formula that forked over a, and we produced an indiscernible sequence along which it was inconsistent. That means it divides. Okay. So the fact that you have some control over which indiscernible sequences witness the dividing means that you can prove things like forking equals dividing. That's very useful. Now, the next thing that I want to prove, this one is a big deal. This is theorem. Suppose T is simple. Then A is independent over A with B, if and only if B is independent over A with A. Okay, so this is that it's symmetric. And this is really something you would hope to be true for any reasonable independence notion. Okay, so how do you prove this? So what we'll do is let kappa be a large-ish cardinal. Okay, what I really mean is that it's like it's a regular cardinal greater than, or it's any cardinal greater than like bet sub omega of the size of t plus the size of a plus or something. But who cares? I mean, just large, okay? Some large enough to apply Erder-Schrader. Erder-Schrader large. So by induction, we will construct a sequence AI, I less than kappa, such that, oh, no, oops, I didn't want this. Such that, okay, AI is independent over everything that comes before, together with B, and AI has the same type over AB as AJ for all j less than I less than kappa. Okay, so how do you do this? This is just easy by extension. So we choose A0 is equal to A, and then given A less than alpha, we apply extension to A being independent with B over A to find A alpha with the same type over AB as A, such that A alpha is independent over A with A less than alpha and B. This is what extension said. Extension says that if A is independent with B, then if I add some more stuff, I can replace my realization with a new realization, which is independent with the new stuff. So this is just extension. Then by Erder-Schrader, this is the same tool we used to prove that Morley sequences exist, if you recall. There is an A, B indiscernible sequence, A prime I less than omega, based on AI, I less than kappa, which means that any finite tuple that realizes a type in the new sequence comes from some other tuple in the original sequence which realizes the same type. So any type which is realized in the new sequence is realized by a type, something indexed by something of the same quantifier free type in the original sequence. Okay, so in particular, this sequence, A prime I less than omega, is AB indiscernible and Morley over A. Okay, so I told you it's AB indiscernible, that's how we picked it. But then the fact that you have this independence here tells you that if you look at this new sequence, because any type which is realized in the new sequence must be realized by something from the old sequence, you also are Morley. What would it mean for it not to be Morley? It means that there's some n such that an forks with a less than n over a. If that's true, then there has to be some alpha such that a alpha forks with a less than alpha over a. And it doesn't. So you're Morley. So we claim that B is independent over A now. If not, then there is some phi xa in the type of B over AA that divides over A. Since phi B A prime 0 holds, Oh, so I should have said that like I can assume that this sequence starts with A. Sorry. So that's, I mean, it's not so important, but of course I can assume it starts with A because every element has the same type as A. So after moving by an automorphism, I can assume it starts there. If it doesn't start there, then there's an automorphism that takes its first element to A, and then just replace it with its image under that automorphism. Now it starts at A. Okay, so because this holds, phi BA0 holds, we know by AB indiscernibility that B satisfies all of these formulas. If you replace 0 with I, you're moving along an AB indiscernible sequence. So of course, phi B A prime I also holds. That means B satisfies all of these formulas. But because phi x A prime I, or let's say 0, divides over A, we know phi x A prime I less than omega, is inconsistent by Kim's lemma. That's a contradiction. And that completes the proof. Okay, great. Now, I just want to mention before we finish one more property, which is called transitivity. And this one I mentioned just because it makes a little more sense than left transitivity. I mean, there's like an intuitive reading to it, which I think there isn't really for left transitivity. So suppose you have A contained in B contained in C. So suppose T is simple, and you have A is contained in B is contained in C. Then if A is contained, or sorry, if A is independent with B over A, plus A is independent with C over B, then A is independent with C over A. And intuitively, this says a non-forking extension of a non-forking extension is a non-forking extension. And that explains why it's called transitivity. Okay, so what does this say? So I have a type over A. I extend it freely to B. Then I extend it freely again to C. Now, the question you might ask is, if I did this in just one step, is that a free extension to C? So if I do a free extension then a free extension, is that a free extension of the original thing? And transitivity says it is. Why? So left transitivity says if C is independent with A over B plus C, plus B is independent with A over A, then C is independent with A over A. This is just a restatement of what left transitivity says. So this follows from transitivity. Or sorry, I'm proving transitivity. It follows from symmetry. Okay. Cool. So now we've got almost all of the key properties of forking independence built up, except for the independence theorem. So next time, I suspect it might take a bit more than a lecture to get there, because we'll have to prove the chain condition first, and then once we prove the chain condition, then we prove it. But the proof of the independence theorem after you know the chain condition is probably a page and a half. So okay, maybe we'll do it in a lecture, maybe we won't. But in any case, it'll happen very soon, and then we'll move on to NTP2 theories, which is much more recent. I mean, NTP2, I think the first real paper on NTP2 came out when I was in my third year of college. That's something Artem did. And, you know, many papers are still being written. So now, I mean, this stuff was like, this stuff that I'm talking about was like hot 25 years ago, 20 years ago. And then the stuff that we're going to be talking about after the independence theorem is like stuff that was cool 5 years ago, and it's still cool. And then we'll get even to more recent stuff after that. So I mean, we're getting quite close to actual research. I mean, that people are still doing, and places where there's a lot that's not known. All right, so that's it for today. I will remind you that we do not have class on Wednesday. So Wednesday is Veterans Day. So I'll still be doing my my Fudan lectures because surprisingly they don't celebrate American Veterans Day in Shanghai, but I won't be doing the normal UCLA class, and that means we'll pick up on Friday. All right. So are there any questions before we end?